Okay, Earth Science Time. Today we're talking about minerals and the formation of minerals. Did I turn the mic on? Yes, it is. Okay. Formation of minerals. Minor Al's mineral collection. Formation of minerals. I think that looks pretty nice if you ask me. Let me make sure the gain is up appropriately on this thing. Okay. What's a mineral? Tricked you. No. Mineral is not.
Sediment of rock. Things that make the rock.
Have you ever heard of a square?
I have.
Good. Okay. Good. I have not. Okay. A square is like a rectangle, isn't it?
Yeah, but a rectangle.
So this is a square. This is the set of all rectangles, actually. This is... Sometimes I think my job is to actively impede students' education so they actually, if they get it, they actually get it. So this is the set of all rectangles, and some rectangles are squares, but not all rectangles are squares. But all squares are rectangles, are they not?
Yeah.
They are. All minerals are rocks, R-O-X, but not all rocks are minerals. Not all rocks are minerals. We sing a song at church that says, "There's honey in the rock." Yeah, and it's a reference to, you would assume, the Bible. What's a rock? This is stuff. Okay, I kind of like that definition. So, not all rocks, let's spell it correctly this time, are minerals. Not all rocks have honey come out of them. Not all. This is a rock. Oops, I had to hide it because it messes with the mic. I have a rock here. It looks like a crystal. This is not a crystal. I'm really glad you said that. This is a rock that I got from the Fort Robinson Museum. It is not a crystal, and it is not a mineral. More on that in a little while. Maybe not in this video, but more on that, if not this one, then the next one. Not all rocks are minerals. Okay, so we haven't actually gotten anywhere. We're at ground zero still. What is a mineral? So what does make a mineral? There are some hints in here, though. What must a thing be to be considered a mineral? Yeah, according to our mathematical diagram, yes, a mineral does have to be a rock. That is true. Let's be more specific. What are the things that make a rock a rock? Let me give you an example. Let me give you an example of a mineral.
Particles of minerals.
Okay, what do you call a particle of a mineral? What would be the smallest unit of a mineral? This, for instance, yeah, okay, so this is made, certainly this is made of atoms, and each of these atoms is made of protons, and those protons are made of quarks, so how far did we go down? But this is not, the smallest unit of this is not an atom. That is, it is made of atoms, but the smallest unit of this is not an atom, because if I just had the atoms that make this up, they wouldn't be this mineral. Even a compound is not the smallest unit of this, because it has to have a, what kind of structure? What kind of structure? What kind of structure that we've already mentioned that my necklace isn't, that this does have, makes it, yeah, okay. It has to have a crystalline structure. Crystalline is an adjective that means referring to crystals. Bring your lab in here, Allie, the one that you guys are making in the lab.
Which one, the red or?
The red one would be better, I think.
They're both not crystals. They're both failures.
So say we all.
Pasted ones that not dissolve salt.
Let me. In the meantime, let me show you this again. Let me also show you. I wish that someone had picked a better Minor Al's rock box.
I said anyone. You said anyone.
You did say that, Mr.
I know. I believe you. These do have a crystalline structure. This one's leaking.
It's leaking.
this is definitely going to be the thumbnail because this is how YouTube works, but it is disgusting. This looks like just like a smattering. Like it looks like a rabbit got run over. Go back and pause it on that. I don't want to hold it up again. The crystalline structure you can see in those different things. Let me draw several different examples of that. In the first one, in the gold-looking one, it looked kind of, and this is a cartoon version of it, but it looked kind of like that. In the next one, it looked kind of more rhombohedral, that is referring to a rhombus. And in the third, this is supposed to be a cube, so you can tell how good a drawer I am. And the third one, we had these kind of hexagonal, they looked almost like, at least to me, they looked like those patterns that form in the mud when it's really, when like the desert dries up, they form this kind of hexagonal pattern. So they all have a different, what are these things? Okay, they're crystals that indicate minerals. They're evidence of a mineral. They are rocks, but these things are all. If these were the only three poorly drawn entities on this board when you came in, we might say this lesson was about what are these? Shapes. Yeah, specifically three-dimensional shapes we call polyhedra. So the structure of a mineral is polyhedral. It has to have, on some level, it has to have a crystalline structure, and that is an arrangement of atoms that is polyhedral. It exists in 3 dimensions, and it has a repeating pattern. Repeating pattern of atoms. The nice thing, one very convenient thing about the study of minerals called mineralogy, I'm sorry, I have forgotten to put this on picture-in-picture. The really nice thing about the study of mineralogy is that the structure of these on the atomic level is reflected in their macro scale, in their visible to the naked eye structure. Let me show you some pictures from the book here. Oh yeah, I do. Look at these. If the structure on the let's say, just for the ease, because you guys already know what this is, and the one that your red one was salt, was it not table salt? So we have what we would have is a.
It was not iodized.
It was. Was it magnesium sulfate or was it sodium chloride? Okay.
Magnesium sulfate. No,
So
it wasn't.
we'll.
No, it was sodium chloride. Yeah, it was.
So we'll say that this dot is sodium, and this dot is chlorine, and they exist in this repeating pattern. You guys have seen a pattern before. You've been to kindergarten. And it's also 3-dimensional, so there might be an orange one back here, a blue one back here, etc. You know what I mean? I'm trying to draw the ones that are supposed to be in the background a little bit smaller, but you see what I'm doing. Like there's a repeating pattern, and the repeating pattern, the unit cell of this, we say. The unit cell here, unit cell is the smallest repeating pattern that represents the mineral, is the unit cell. In this case is shape.
Square. Cube. Right.
Cubic. It's cubic. So sodium chloride, the mineral halite, has a cubic crystalline structure. That's one of the properties of a mineral. Its crystalline structure. It has a definite crystalline structure. What other things might be true of a mineral that we could use to identify, that we could use to say whether it is or is not a mineral? Crystalline structure is one. What else must it be for it to be a mineral? Let me give you some non-examples. Is that what the girls made in the lab, is that a mineral? Have they made a mineral? Why? You already know the answer is no. You feel like it should be no. No, that's not it. Why? Why is it not a mineral?
It didn't have no shape to it.
It-
It was flat.
No, that is not it. Can Kyler and Allie make crystals?
No.
No. Well, they can try their hardest. Can they make crystals? The answer is yes. They can. They are physically capable of making crystals. Can they make minerals?
No.
No. Why?
Because minerals are what makes crystals.
You try.
I don't know. I was going to say it's a non-renewable resource.
You try, Lily.
Can't make it because they made by Earth, not by you.
There you go. That's exactly it. They have to be. They have to be naturally occurring.
That's what non-renewable resources are.
I think 2 C's and 2 R's. Is that right?
I think so. I think we decided it was. I think we decided it.
Yeah, we decided that occurring is 2 C's and 2 R's. Haley's almost right. She says a definite chemical composition. Or is that what you said? You said something like that, right? Yeah, they have to have. Definite is not really the word we want to use, because definite means like water is H2O. It's always H2O. Every H2O is always water. But there are some minerals that we would still call. I'm trying to think of one that's an example, like that alum has both potassium and aluminum, and they switch each other out. And so it's not a definite crystalline structure, it's not a definite chemical composition. We call it a specific chemical composition.
What ghost figure is just here?
A specific chemical composition. Now, I wish someone had brought me some seashells, but is a seashell a mineral? A seashell is made of calcium and carbon in not quite cubic, but a rhombohedral pattern. They do have this pattern of calcium and carbonate, the carbonate polyatomic ion. Is that a mineral? No, it isn't. Why? What's different about a seashell? Is it naturally occurring? Yeah. Does it have this crystalline structure? I just said it did. Does it have a specific chemical composition? Yeah, CaCO3. What makes it not a mineral if the seashell made it? Or if the little critter made it? Has to be inorganic. I prefer abiogenic. Let's break that word down a little bit. What's a mean? Not. Bio? Life. Genic, from the same root as Genesis. It doesn't come from life. It doesn't begin at life. So abiogenic means it isn't made by a living thing. You can see these two things are not mutually exclusive, but it kind of makes this one a little bit redundant. You see what I mean? Like if it's abiogenic, obviously human beings didn't make it because human beings are alive. But yeah, we consider it to be those 4 things. Yeah, those are the 4 properties of a mineral. All minerals are these things. We can even say this is the definition of a mineral. Now let's give some non-examples. I already said a seashell is not a mineral because it is not abiogenic. That is, it's biogenic. It's made by life, and so it doesn't count. What's another non-example of a mineral? Non-example meaning I don't know how to describe that. That's an example of that it's not. What's another non-example of a mineral? Something that an idiot might think is a mineral, but it actually isn't because it's not abiogenic. Give me another example. Lamp. Is that what did someone say lamp? Okay. Mulch. Bless you. Yeah, okay. Okay, so an idiot might think that mulch is a mineral. It's because, I mean, really though, you're right. Because like if you had 2 words to say what a mineral is, and you had to say it to you. Stop. We're trying to have a professional video here. Not mulch is not how we define. Yes, I thought they were until you just said that. If you were trying to tell a kindergartner what a mineral is with 2 words, and you said on ground, I mean, you could come up with worse definitions than that. The mulch, the kid would take out of their mouth a piece of mulch they were chewing on, and they would say, mineral? And you would say, no, because a mineral is not, you would say this to them, no, a mineral is not a mineral must be abiogenic, and that mulch was produced by a living thing, a tree. And they would say, and then they run away and eat something else. That's what kindergartners do. But give me another, now tell me a non-example of a mineral that doesn't have a specific chemical composition.
Glass.
I like that. That's really good. That's really good. Great job, Allie. Glass. Yeah, glass as a category of materials does not have a specific chemical composition, and therefore that's not a mineral. What's one that isn't naturally occurring? Give me an example of something that people might think, even a reasonable person might think is a mineral. No, naturally occurring. We have to find one that people might think is a mineral, but actually isn't because it is not naturally occurring.
Plastic.
Maybe. Diamond. Yeah, there are synthetic diamonds. They can be better in every observable way than a natural diamond, but they're not technically a mineral because they're not naturally occurring. And when I say better, I mean the 4 ways that we rate diamonds: color, clarity, another thing that I forgot. Color, clarity, carat, which is its weight, and another thing. It maybe cut is the 4th one. I don't remember. But there are 4 C's of grading diamonds, and human beings can make better diamonds in every single area, and they still are not minerals because they're not naturally occurring. Now, I have a great example for this one. One that people might think is a mineral. In fact, people today, just now, not idiots, have thought is a mineral, is my necklace. This is not, it even looks like, because of its shape, it even does look like, this is how I take off my... No, I'm saying not idiots. I specifically said not idiots. Because of its shape, people do think it's a crystal because it's cut that way. But this is not a mineral. I bought this one specifically. Well, I bought it because Asher said that one's cool. But it is not a mineral. This is a rock. What I have here is a rock. My little crystal necklace is out here in the area that are rocks but not minerals because it doesn't have a crystalline structure, because it is obsidian, which is not a mineral. Obsidian, as we'll learn about in the next video, probably is a rock. Now, speaking of obsidian and minerals both, even though obsidian isn't a mineral, how do minerals grow? What does it mean to grow? What is growing? Big. Yeah, get big. Grow means get big. How do minerals grow? I thought that growth was one of the properties of life. Isn't growth one of the properties of life?
Shut up, Reba.
Answer me, please. Isn't growth one of the properties of life? Yeah, it is. Do only living things grow, though? Obviously not. Crystals grow. So minerals grow. They get bigger. Their pattern on which they are built repeats, and that causes their growth. There are 2 main ways from which minerals grow. Tell me them. What are the 2 main ways from which minerals can grow?
Seed oil.
Not seed oil, no.
Minerals can.
Okay, how is the mineral growing in our lab growing? From what?
The sun. Except they're not.
No, it's not photosynthesis.
Temperature, air.
No.
Musty.
Okay, that's close. What did you say? What did you say, Cyrus? Yeah, okay, so from solution. So basically, the constituent elements, that is the elements that make up that mineral, the constituent elements of that mineral are dissolved in water, and then when the water evaporates, the minerals grow together. The crystals, it crystallizes from that solution. The other one, now that we know that one, what would the other one be probably? From what? No? It's another way that minerals grow that we cannot replicate, or we probably won't be able to replicate in the lab very well.
Erosion.
No? It's part of the point of you're doing a lot of these labs that were not about actual growing crystals, but about instead the heat of planet Earth, because they grow from,
Thermal energy.
yeah, what do we call it? When rocks and minerals get real hot, and they melt, and they're no longer magma. This is like pulling teeth. Magma. Magma is the answer. From magma. In both of these cases, the longer the mineral has to grow, the what?
What's the first?
The longer the mineral has to grow, the what it gets.
The bigger it gets.
The bigger it gets. This is extremely, it seems basic, doesn't it? I mean, it's true of kittens, right? If you stomp a kitten, it's done growing.
But minerals don't die.
No, but they do. If their growth is stopped, how would these things growth stop? Not from being stomped, but how would the growth of this one, how does the growth of yours stop? It runs out of water, okay? How would the growth of this one stop? Yeah, it runs out of heat. It gets too cool. So in both of these, the growth will stop. The growth does stop, but the longer it has to grow, the bigger it gets. So let's engineer a way that these girls' crystals could grow bigger. And in fact, I have some examples. Payne, would you hop up? And above the water distiller in there are some little like plastic containers that have crystals in them. Would you go get one of those for me, please? So how could we engineer a way for these girls that their crystal could get bigger? It's almost done growing, and it's never going to get much bigger. But how could we redo that lab so they do get bigger?
Add more water.
More water and make it so that it takes longer to dry out by putting in the fridge, probably. Yep.
Or
Where on planet Earth? Where on planet Earth of the have we talked about the layers of planet Earth this year at all? Oh, we did in the last one because when the Earth was coalescing, the heavier elements went to the center, which gave the Earth a what? What's in the center? Core.
somewhere, I think.
Let's call that the inner core.
Outer.
Okay, and then we have the outer core around that.
And then the mantle. And then the crust.
Outer core. We'll put the mantle in brown.
It's way bigger.
Mantle in brown. And we'll put sure. And the crust, actually, something that I heard about the crust that I always kind of memorize is that if you think about, thank you, don't do that. I have to cut that part now. This crystal, by the way, this was grown 2 years ago by earth science students then, and it got a lot bigger because it took longer to grow. It took longer to grow. They gave it more time to grow. I really like this. Don't open it because I think it's kind of poisonous, but do pass it around. And then check this out. Here's my other demonstration besides what we're going to do with the mineral identification. But here, hey, if this is planet Earth, the thickness of this skin compared to the rest of the apple is almost exactly the same ratio as the thickness of the crust of Earth compared to the rest of Earth. Since like 8 o'clock this morning.
Did you rinse it off before you put it in your drawer?
I wash it at home.
Mr. Kyle,
But you put it in your drawer and then put it in your mouth.
Mr. Kyle, it may have just gone out of the container.
Please pick it up as best you can. It's not actually poisonous. It's just this is a magnesium sulfate crystal too. I was just trying to scare you, but none yet. Now that wipe up.
That it was even made in the first place.
Now go throw those away. Go wash your hands. Bring some wet paper towels back and wipe up the little mess. It's not actually poisonous, but I really wish it wasn't broken still, of course.
My bad. Maybe just get better.
Anyway, let's dial the chaos down from 11 to 8 for a second, Kyler. Shh, listen. So the crust is the narrowest part of the Earth, and not. Oh man, this whole thing is off the rails. Instead of posting this video, I think I'll just repost one of the ones that I did from before. But the crust is about the same ratio of thickness to the rest of planet Earth as the skin of an apple is to the apple itself. We also need to know these words. The mantle has this kind of like dividing line halfway through it where this part, the crust and the upper part of the mantle are called the lithosphere. And the lower part of the mantle is called and you need to know this, so I don't know why you're not writing it down. The lower part of the mantle is called the asthenosphere. I will spell that again out loud. It's ASTHENO sphere. So the point here being that the lithosphere is that part of Earth that generally behaves as a solid. Lithos is the Greek word for rock. The asthenosphere is the part that behaves mostly as a liquid. It actually behaves what we say as a plastic. It deforms in a plastic way. And we call it, the asthenosphere is what we call that part, and the asthenos is the Greek word for weak, that it behaves kind of as a liquid, that it has a weak response, you might even say if you're Greek, to stress. Yes?
Can I also pour us tea?
Sure.
Because tea is made from minerals.
Now, the point of this is that whence come the heat of planet Earth? Where does the heat come from? The core. Well, I mean, that's kind of a little bit facile, but the core is certainly the hottest part of planet Earth, and it radiates outward, making it the subsequent or the progressively further from the core places cooler. But where did that heat come from in the first place? Two main sources. Give me one. No. What makes the core hot? When did the core become hot? When it was forming. So as the billions of years ago, 4.5 billion years ago, when the Earth was forming, when the Earth was particles accreting in the solar system, right? Particles of various sizes accumulating together like Play-Doh lumps. The friction between those heated them up, right? Remember, when the Earth was first formed, it was all behaving as a molten ball of magma because of the heat of those collisions and the gravity pulling them together. Now, one of the reasons that it has continued, that they're not still doing that, the Earth is not still, there's a little bit of tidal force drag between them, but one of the reasons that it stays hot is that there are what decaying in Earth's body? Yeah, alpha decay is one example. No. It's what, though? What kind of elements that decay? Yes, radioactive decay. Radioactive decay. So radioactive decay, as it were, keeps this hot. That it became hot at the beginning when it was all forming, and the reason it stays hot is because of radioactive decay. Radioactive decay. Let me spell one thing right in my entire life. Radioactive decay provides thermal energy. All this to tie back to, how do we get bigger crystals in this kind of thing? Take longer to dry. How do we get it in this kind of thing? Take longer to cool. Now where here, point A, or here, point B, is going to take longer to cool? A will take longer to cool because it is warmer. So we have crystals that form inside of Earth are larger than those on the outside. We'll talk about this again when we talk about igneous rocks. We call those intrusive and extrusive igneous rocks. But basically, the bigger crystals, as a rule, but rules can be broken. It's like a rule of thumb, really. There are exceptions to this. But bigger crystals form in warmer places, generally. Do you know what it means to be a mineral? Yeah, we talked about that. It has to be naturally occurring, abiogenic, crystal structure, specific chemical composition. Then, how do minerals form? Well, they form from solution or from magma. And now let's list, does anyone still, this thing was kind of a little side dish because we had talked about it before, but does anyone still need this or anything that's up here already? Do you have this written down, Cyrus? Good. It seems like maybe you don't, but it's okay. Thanks for lying to my face. Well, yeah, let's wake up and let's write some of this stuff down, please. What are the properties of minerals? Why is it important to know the properties of minerals? Are the properties of this and this the same?
No.
How? Where? No, they're obviously not, because what's one of the properties? Well, how do you know even from there that these two are different? Not necessarily that there's different minerals, but how do you know that these two things have different properties? You can see it. They look different. So yeah, so the properties of minerals are important to properties of minerals help us differentiate between them. Color. You know what color is. Color is also the most useless way to differentiate between minerals. It's the most useless. Why? One mineral can have a whole slew of different colors. My obsidian is a rock, not a mineral. But obsidian, even though it's a rock, comes in black and green and red and all different colors. So one mineral, or rock, can have all different colors. And almost any mineral can be black. Some of them, by definition, can't. But you see what I mean? Like it's useless in both directions. One mineral can have lots of different colors, and lots of different minerals can have one color. So we almost never just use color. It's not good enough to say, oh, I know it's sphalerite because it's silver, because not every instance of sphalerite is silver, And not every silver mineral is sphalerite.
Density.
Density. Let's just write this from physical science. You should already know this. Rho equals m over v. Density equals mass divided by volume. We do sometimes, you should know this, we do sometimes use the idea of specific gravity for this, which all that is just comparing the density to the density of water, which is 1 at 4 degrees Celsius. And so it's basically just dividing it by 1. That way we can have a unitless number for density, because sometimes that's important.
What's that P looking letter?
Rho. This is the Greek letter rho.
Rho.
If you look it up on Google or something, it'll look like this, probably a little bit nicer. I always make mine kind of slanted and spirally so that you can tell it's not just the letter P. In so much as that means anything with my handwriting. Color, density, we have luster. What's that word mean?
Shininess.
Shininess. What else? What other properties do minerals have?
Isn't there a scratch up there?
Streak. You mean streak. And that's the color of the powder. Because that's really what we're doing. When we streak a mineral, here I have a streak plate, here I have a mineral, here I have a streak plate, here I have a streak plate, which is made of unglazed porcelain, here I have a mineral. What I'm really doing as I streak it is I'm grinding it into a powder. That you can't really tell, but that's also what you're doing when you write with a pencil in your notebook, because you're grinding that graphite into powder, and the powder is staying behind, even though the graphite is a mineral. Yep. So this is called streak. We're actually identifying, and that's, you can see what color. If this is what color? Okay, here's another problem with color. Someone said green. I might say magenta. It's different. Yeah, purple. There's some subjectivity with color. I would say gold, probably. But the streak for a given mineral is generally the same color. So that removes half of it. There still are multiple, this one's gray, there are multiple minerals that do have a gray streak, but all instances of this pyrite will have a gray streak, or roughly a gray streak. So it removes half of the problem of color. You can pass that around and do your own streaking if you want. Nice. That's gross. Okay, no, I'm just kidding. You do you. No, just keep it there. What's another property of minerals we could use to tell about them? Hey, what's another property of minerals we can use to tell what they are?
Hardness.
Hardness. How hard it is. For this we use the Mohs scale of mineral hardness, where 1 is the softest, or we don't really say it, 1 is the least hard, and 10 is the hardest. Mohs scale. M-O-H''S. And then crystal structure, or what we sometimes call crystal habit. This is the best one, because remember, this is one of the things that defines a mineral, is that they have a crystal structure. And every mineral has a slightly or maybe completely different crystal structure. I don't mean that it has a different crystal shape, but when we include what elements make up the crystal structure, that's what makes it that mineral. So this is the best one, and we use these kind of side effects of cleavage and fracture as like, I don't know what you'd say, like as proxies for crystal habit. Cleavage is how it breaks along its crystal boundaries, and fracture is how it breaks not along its crystal boundaries. So if I, let me see, I don't really like to break these, but a pretty easy one and good one to break is this biotite mica. We say it has perfect cleavage on one axis, which means that it will break perfectly along its crystal line on one axis. And I can show the camera here. This is mica. I can peel off just a tiny little flake of it, and that's called cleavage. So I've cleft is the verb. To cleave means to break. I have cleft this mineral. I have torn it apart along its crystal lines. So that's cleavage, is when it breaks along those same lines as its crystal, and it's fracture if I break it along the other axis. If I just break it like that. Let me give you a bigger demonstration of that. If I have a stack of rosters from Mr. O's biology classes, this represents that mica. So the crystal structure of mica is like a stack of paper. And it has kind of weak bonds that hold them together and fairly strong bonds. So the cleavage in this case is when I peel them off like this, right? That's breaking along the crystal line. So there's a crystal structure that holds these together. And to break it like that, right, that's cleavage. If I do like this, that's fracture. I'm breaking it across the crystal line. So does that kind of make sense? Of ripping?
Yeah.
Not a bad noise. It's a lovely noise. So these tell us about the crystal habit, and that's very important because that defines what that mineral is. Some minerals have special properties like magnetism or fluorescence or effervescence, which is where it bubbles in response to acid. But those things are not maybe unusual, but we don't need to know them for all different minerals. Now, quickly, the last thing we'll talk about are the categories of mineral. Oh, and by the way, you will do a lab with these. You'll become much more familiar with these hands-on because you're going to do a lab with them. But now let's talk about the categories of mineral. Probably the most basic category of mineral are the elemental ones, the ones that are just one element. Like a chunk of raw gold found in nature, remember, it has to be naturally occurring, and with a crystalline structure of just gold that you might find. We don't really find this anymore, just like gold nuggets lying around. In the olden days, people used to. Like, you'd just be walking along and there would be a lump of copper there for you to trip over. That doesn't happen anymore because copper is fairly valuable, and all the copper that was around to just be tripped over has been tripped over and then taken and used. But just plain elements, so like gold and copper. We have oxides. Oxides, which are some element combined with oxygen. So like calcium oxide or iron oxide, which we might call hematite. This is the mineral hematite. By the way, these ones would just be the mineral gold or the mineral copper. We would usually say native gold or native copper. Calcium oxide, let's erase that one because that doesn't really exist in nature all by itself. I'm trying to think of another oxide that we could use. Uranianite, it says. UO2. Uranianite. Do you notice a trend in mineral names? What do they usually end with? No? Ite. Yep, ite. Carbonate minerals are really important. Calcium carbonate is usually called calcite, although there are... I put hematite. You don't need to know the mineral names. I'm just giving you examples. Carbonate minerals have this carbonate group here, CO3, attached to them. Sulfides, sulfates. Wait, last thing before you go, I'm going to put a ... because there are more, but the most important one are silicates. And they all have the SiO4 2- ion as part of them. They're the silicates. Silicates is how I say it when I'm talking fast. Silicates is how you might say it if you were being really specific. But the silicate minerals, SiO4 2- is the group they all have. In fact, they're so important that we usually call these other ones non-silicates.